Welcome back. Back once again with the Renegade Master, Math Instructor, power to the people. Okay, we're going to do polynomials, graphs of polynomials specifically. We talked about what a polynomial is in 5.2. Now we're going to see what they look like on a Cartesian plane. First thing we can do is say, whenever I draw a polynomial, whether it's a quadratic, quadratic, or a cubic, or a quartic, that's what those kind of generally look like. On any of these graphs, I can split this plane into two parts, near and far. I'm going to call this one local, and I'm going to call the outside, oh, you know what? I'm going to do local in green real quick. I'm going to call the inside local, and I'm going to call the outside the end. And what differentiates them is that the local contains all the roots and all the turning points. Whoops, that's the wrong spot then. So I have to go past here and past here. So the local behavior is where all the roots and all the turning points live. And since I can only have so many roots and turning points, I'm going to run out, and I'm going to be able to get past that either on the left or on the right, either one, both, and say, now we're in the end. So once we're in the end, all of the roots and all of the turning points are done. They're all left behind. So when I talk about graphs of polynomials, I want to talk about the local part and the end part. So let's talk about the local behavior. And then we'll talk about the end behavior, and then we'll come back and talk about the local behavior some more. It'll be great. Remember last class we had a degree 4 polynomial? And that means since it's degree 4, it has to have 4 linear factors. Now last class, the one we had a doubled up factor. It had x minus 1 twice. But if it didn't, then each linear factor would be a root. So we can have up to 4 roots. Sometimes they double up or triple up or whatever, but you can have up to 4 roots. Now this next bit is not exact, but generally I want you to think of it like, oops, that's not where that goes. Oh, it's like the one I drew up there, right? Maybe here's the 4 roots. If you have all of your roots, then your turning points are going to happen one between each root, because it has to hit the root. At every root, it's going to like cross over, right? And then it has to turn around to get to the next root, and then turn around to get to the next root, and then turn around to get to the next root. So if you've got all 4 roots, then there has to be a turning point between each one. But the weird thing is, then you're out of turning points. There's a calculus reason that you're out of turning points, but I'll just say you always get 1 fewer turning point than you have root. So, well, sorry, 1 fewer turning point than the degree. So there's up to 3 turning points. So this cubic up here, it can have up to 3 roots and up to 2 turning points. The quadratic can have up to 2 roots and only 1 turning point. And that turning point, well, that turning point is known as the vertex, the vertex. So if I were to draw a ridiculous polynomial like degree 9, we would have up to 9 roots and up to 8 turning points. So a degree polynomial could look like 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, right, it doesn't draw as I count, but I counted out 9 roots, right? So the roots, the 1, 2, 3, 4, 5, 6, 7, 8, 9. And between them are turning points. 1, 2, 3, and 4. 8 turning points. Now it doesn't have to look like that. Sometimes it's missing roots and sometimes the turning points are on different sides, but if you know the degree, then the number of roots is the same as the degree or less, and the number of turning points is 1 less than the degree or less. The calculus reason is because each of these turning points happens when the graph is flat. And when I say flat, I mean the instantaneous rate of change is 0. And it turns out the instantaneous rate of change is a polynomial whose degree is 1 less than the degree of the original. So that turns out to be the calculus reason. But for us, we can just remember same as the degree, turning points are 1 less than the degree. So that's all I want to say about the local behavior for now, because the end behavior is pretty simple. Let me cut this off here. Look what happens in the end. All the roots and all the turning points are local. So when I'm in the end, by definition, I have run out of roots and I have run out of turning points. So we can't cross the x-axis. And we can't turn around. If we can't do either of those, all we can really do is zip off in one direction. So the end behavior is really simple. On the right, we either zip off up or zip off to the down. On the left, we either zip off to the right or zip off down. I think you can see examples of all of those behaviors up here. It could go both up, or they could go one up and one down, or they could go both down. So there's exactly 4 options. For a polynomial, there's only 4 things you can do. Once we get out to the end, let me draw 4 graphs. The local can be any kind of ridiculous twists and turns, but once you're out in the end, they could go both up. They could go one up and one down. 2 different ways you could do that, of course, left or right. Or they could go both down. These are the 4 polynomial end behaviors. There are only 4 options. So how do we decide which one? Well, the key is, where is the end behavior? Little values of x are in the local. Big values of x go in the end. So if I want to know which way it's zipping off to, I can just pick really big positive and really big negative values of x and see what happens. But there's an easy... So if you wanted to, you could just evaluate your polynomial at positive a million and negative a million, and you'd be pretty much guaranteed to be in the end behavior. Not a lot of polynomials have roots or turning points out past there. Some of them do, though, so you might want to find all the roots and turning points before you do that, and that sounds like a chore. Good news is there's an easier way. Let's talk about what happens when x gets big. Specifically, I want to say x is moving out in these 2 directions, however far. Remember before, I called the ends of the arrow positive infinity and negative infinity? And those aren't real numbers, but they represent each end. And in the end, way out past the local behavior, that tiny slice in the middle, I'd say x is moving toward each of these with an arrow. So I'd say on the right side, I'd say x is going toward infinity. And on the left side, I'd say x is going toward negative infinity. Now, when that happens, let's take an example polynomial, and I'll show you what happens to the whole thing. I know what the input's doing. It's getting really huge in one of 2 directions, but what's the output doing? Let's say f of x is 2x cubed plus 9x squared plus 4. So for local values, anything is really fair game. Like if I plug in x equals 1, I'm going to get 2 plus 9 plus 4 is 15. If I plug in x is 0, I'll get 4. If I plug in x is 2, I'll get some other number, 48. So I don't really know what it's doing there, but I can pick ridiculous values. Now look what happens. Let's say x equals 10, or x equals 100, or x equals 1000. And let's see what happens to this polynomial. So let me do the 3 terms here. This one will be 2000 plus 900 plus 4. And this will be 2 million plus 90,000 plus 4. And this will be 2 billion plus is that right? Oh yeah. Plus 9 million plus 4. Now look at it this way. 900 is 45% of 2,000. 90,000 is only 5% of 2 million, and 9 million is only half of a percent of 2 billion. So, as time goes on, the leading term is getting bigger and bigger and bigger, whereas, relatively speaking, the rest of the polynomial is getting smaller and smaller and smaller in comparison, to the point where if I go out to 1 million or 1 billion, the output is almost entirely determined by the leading term, and the rest of the terms of the polynomial, no matter how many they are, can't even make a dent in it. And the same thing happens if I had picked negative numbers instead. If this were negative 1,000, then I would have negative 2 billion plus 9 million plus 4. And that's like, okay, that's almost the same. It's the same thing. The leading term, we say it dominates. I'll write this as x goes to infinity or x goes to negative infinity, so as it gets huge, the leading term dominates. And what that means is the output is the sum of all these things. So here the output would be 2 billion, 9 million, and 4. But the thing is, the output's the y-coordinate, and if the rest of the terms are like less than 1%, then it's like, let me put it this way. Here's the graph of just the leading term, right? So here's the graph of just the leading term, green graph. And now the rest of these are going to change the value by like, well, at first it's 45%, but out here it's like less than 1%. So here's the graph if I include all the terms. It's going to have some wiggles and wobbles in the middle. And then by the time we get to the edge, it's going to be almost exactly the same. So it's weird in the local behavior, but by the end behavior, it looks pretty much exactly the same, less than 1% off. It certainly can't go the other direction from the leading term. So the moral of the story is, if you graph the leading term, you're going to get the local behavior wrong, but you'll get the end behavior exactly right. So all I have to do is figure out, what does the leading term do? And then I will know what my end behavior is. Now, the leading terms are really simple. The leading terms are just power functions. So the leading term determines the end behavior. And the leading terms are just power functions. Now, what do power functions do? Again, those were k, x to the p, right? So k is mostly just a stretch or a shrink. The only interesting thing is if k is a flip. But this x to the p, oh, we've studied these. We studied these in graph transformations, 3.4. I know that x squared looks like this, and x to the 4th looks like this, and x to the 6th looks like this. This is x squared, x to the 4th, x to the 6th. The thing about these even functions, these are all the even functions, is that they have horizontal symmetry. So this is where p is even, and when they have horizontal symmetry, it means both branches go the same way. All of these go up, but if I made k negative, so here's negative x squared, then they both go the same way, but it's down both sides. They have to go the same way because they're reflections of each other. And it can either be not flipped or flipped. Meanwhile, same thing happens, but with the odd functions. Here's x, and here's x cubed, and here's x to the 5th. All of these have rotational symmetry, which means one end and the other end have to go opposite directions. They can't go the same direction. So if it's not flipped, they look like this. And if it is flipped, Well, here's the graph of, I didn't draw that right. Here's the graph of negative x cubed. If it's flipped, it'll go the other way. So like I said, there's only 4 end behaviors, and here's how they look. You decide, does this polynomial, is the degree even or is it odd? If it's even, then they go the same direction. So then I check the leading coefficient. If it's positive, then it's going to be like x and x squared. It's going to go both up. If it's negative, it's just the same thing but flipped. Meanwhile, if we're looking at odd, I check the leading coefficient. And if it's positive, then it looks like x or x cubed. It goes up to the right and down to the left. And if it's negative, well, it's the opposite. It'll just be the same thing but flipped over, so up to the left and down to the right. So that is how you decide the end behavior of a polynomial. You only need to look at the leading term. You just check the degree and the leading coefficient. The degree tells you whether it's whether the leading coefficient has even symmetry or odd symmetry. And then the leading coefficient, if it's negative, there's a flip. If it's positive, there's no flip. Just a little notation. This graph right here, I could write something like, as x goes up to infinity, so as x moves out to the right, as x goes out to the right, y is getting bigger and bigger and bigger, bigger and bigger and bigger. So as x goes to infinity, f of x also goes to infinity. And over on the left, as x gets further and further to the left, as x goes to negative infinity, f of x still goes to positive infinity. One more example. If I had this graph, I could write, as x goes toward infinity, and now f of x is going down, 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 f of x goes toward negative infinity. And over here, as x goes to negative infinity, f of x is going up, 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 so f of x goes to infinity. These arrows, this is called limit notation, and sometimes they like it when you write the answer in limit notation. It'll help you if you study rational functions. I want to say rational functions, this will help you. Oh, wait. We study rational functions, don't we? That's a part of this class. That's in our curriculum. Okay, this notation will come in handy in section 5.6. Wow, now I don't remember if rational functions are part. I think they are. Well, we'll find out soon. By now, you already know. Hold on, you know what? Let me check the syllabus real quick. I've been logged out of Courseden. Of course I have. Introduction, syllabus. If the syllabus says we're doing rational functions, then we're doing rational functions, but I honestly don't. Syllabus does not say rational functions. Thank goodness. Okay, we are off the hook. Class, we are off the hook. The reason I say thank goodness is not because I dislike rational functions. They're okay. But it's that I'm trying to marathon all of my lectures tonight for Unit 3, and that's a long one. So, oh, thank goodness, I just have to do this, and then division, and division's easy, and then theorems, and theorems are really fun, even if they're not easy. So, okay, I'm gonna make it. I'm gonna get through this. I'm gonna get through this. You can do it. Believe in yourself, Nathan. Okay, so end behavior. Let's say I told you that, wow, I'm really getting my second win here. F of x was 10x to the 19th minus 3x to the 8th plus x to the 4th plus 2. I just want to know the end behavior right now, and the secret is that none of this crap out here matters one bit to the end behavior, because 10x to the 19th dominates. So all I have to do is say 19 is odd. So we're either going like this or like that. And then 10 is positive, so we're going like this. Since it's positive, we're going to be just the same as like y equals x or y equals x cubed. This is how a regular odd function looks. This is how a flipped one looks. So there you go. It's a real easy process, you see. Did that. So now I just need to say a couple more examples. If I told you that f of x was negative 42 x to the 999th plus a million other terms that don't matter because this one dominates, then all you have to do is say, okay, or here, you know what? I did this already. Let's make this one 998. I'd say 998 is even, so we're either going both up or both down. Negative 42 is negative, so there is a flip, which means we're choosing this one. And so that's the end behavior. If I wanted to get fancy, I could say, as x goes to infinity, f of x goes to negative infinity. As x goes to negative infinity, f of x goes to negative infinity. But I'm not going to write that because my wrist is already starting to hurt, and I've got 2 more of these to bang out tonight. So, one more. Here's a trick question for you. Pause the video and see if you can get it. Let's say f of x was, I don't know, 4x to the 8th minus 3x to the 9th plus 2x to the 7th plus 5. Can you tell me how that looks? Okay, unpause, and the answer is 4x to the 8th is not the leading term. It is utterly and completely dominated by negative 3x to the 9th. And I'm not going to crack any jokes about that. So 9 is odd, so we've got a wibbly wobbly like so or like so. Negative 3 is odd, so instead of looking like y equals x, that's if it's positive. Instead, it's going to look like y equals negative x. This is how you can remember, because it's negative. So our end behavior is going to be this one. As x goes to infinity, f of x goes to negative infinity. As x goes to negative infinity, f of x goes to infinity. Anyway, it's just this notation here. Sometimes my open math likes it, but I think there's one of those on your final. One of those with this notation here. So don't forget about it, but it's like, it's not the most important thing in the world. Just don't get hoodwinked if I put the leading term somewhere it don't belong. Because this polynomial ain't in standard form, but we can still do all the same stuff. Okay, that's it. That's the first part of this video. In the second part, I'm going to be telling you more about the graphs of polynomials. Hope to see you soon.